the backward algorithm for the hidden Markov model is very similar to the forward algorithm. Remember that for the forward algorithm, we computed those alpha quantities from alpha 1 to alpha 2, alpha 3, and so on up to n. So we were going in the forward sort of direction. And for the backward algorithm, it turns out that we're going to go backward. We're going to compute some value starting at n, and then we'll do n minus 1 and so on back to 1. And it's going to be very similar to the forward algorithm. So the setup is, remember, we're given some x's, and so we're given some x's, and we assume those distributions. We assume that we know the emission probability distributions, the probability of the x's given the z's, and we assume that we know the transition probabilities from going from zk to zk plus 1, and we assume that we know the initial distribution on z1. And the goal for the backward algorithm, which we talked about before, is to compute the probability of xk plus 1 through n given zk. And we want to do this for all k from 1 to n, and for all, so this is all k from 1 to n and all zk, for each of those k's, all the possible values of zk. And we were assuming here that zk took values 1 to m. That's an m, that's an n there. K is going from 1 to n. Okay, so we want to do that. I guess actually n minus 1 or something like that, but you get the point. All the k's that matter. Okay, so how are we going to do this? Well, let's take the same approach. Remember, we talked about the sort of general purpose way of tackling this kind of thing is to try to set up a recursion. So let's try the same approach. See what happens. So we want to get something that looks like this. We're going to start with this, and we want to sort of just use the rules of probability to try to expand this. Maybe we'll use a sum like we did before to try to expand this and use the Markov property and use these distributions that we are assuming to get this in some sort of, for a different k. That's typically the thing that you do when you get it for a recursion. We want to get this for a different k. So let's think about here, what is the situation? I drew the graphical model here for illustration purposes to see. And so here, what do we have? We have k plus 1 through n, so that's all this stuff here. And we have zk, so we have this guy. So what would be helpful here? Well, it would be kind of nice if we had this guy, if we introduced this guy, because then we could factor off the transition probability here, and we could factor off the emission probability here. So that looks fairly promising. So let's do that. Let's introduce that guy. We can always sum over zk plus 1 from 1 to m, all the values that he takes, xk plus 1 to n, and zk plus 1 given zk. And now let's see if we can make a little more space. This might be kind of a long line here. Summing over all those, let's try to factor this in a way the way that we talked about there. So first we want to get this transition probability here. So let's try to get that. So let's see. So that's going to be something like probability of zk plus 1 given zk xk plus 1 to n. Actually, but wait, let's see. I would want to use the conditional independence properties to reduce this down to the just zk plus 1 given zk, but let's see. But zk plus 1 is not conditionally independent of these given zk. Let's try a different approach. So let's try something a little bit different here. Let's try instead. Let's try to get something like this first. So let's try to pull off xk plus 2 to n given zk plus 1. So we're going to do it for the next higher k. So we're going to condition on zk plus 1 and xk plus 1. We also still have zk hanging out here. Xk plus 1 times, so let's see, is that going to help us? So there's going to be more, but xk plus 2 is going to be this part to n, given zk plus 1 and zk, and so I want to say that this is conditionally independent of these given this in order to get something that looks like this. So we can drop these guys out, and that is going to be the case. Okay, so that's looking good. We'll come back to that in a sec. And then we have the probability of, what do we have? We conditioned on this stuff, and then we have the probability of, let's do xk plus 1 given zk plus 1. That will be good, because then we can use conditional independence here. And then lastly, we have zk plus 1 given zk. And that's nice, because now we have just the transition probability. Okay, so let's come back to this one. So we said here, maybe we'll do red here. We want to say that this is conditionally independent of these zk and xk plus 1 given this guy. So we're given, so we condition on that guy, and so d-separation, so this is a tail, oh no, red. This is the tail here, so there's a stop sign here and a stop sign here. So any path from any of these guys to any of these guys, it's got to go through this stop sign here. So these are in fact d-separated, and therefore they are conditionally independent given zk plus 1. Okay, so that's good. So we can do that, and then we have something which looks like that. And for this one, what do we have? We have xk plus 1 given zk plus 1 and zk. So we'd like to say, we'd like to drop the zk. So we'd like to say that this is conditionally independent of this given this. And since we're given that, just to be pedantic again, we're conditioning on this guy. So we have a stop sign here, and any path from here to here, well, there's only one path. So the path is blocked. So these are d-separated given this guy, and therefore they are conditionally independent. So let's go back to here, clean that up, and we can drop zk, conditionally independent. Okay, so now let's define some things. Now we're in pretty good shape here. Let's call this, what do I want to call this? Let's call this depends on zk. Since we're assuming the x's are all known, we won't make that dependence explicit, and it also depends on k. So let's call it beta sub k of zk. Those are the quantities we're interested in. So this is, what is this? That was k plus 1, this is k plus 2, that was k, this is k plus 1, so this is this is beta k plus 1 of zk plus 1. It depends only on zk plus 1. This is the emission probability. That's known. And this is the transition probability. And that's known. So this is super simple, right? I mean, it's just a one-line derivation. Well, 2 lines on the screen, I guess. 1 line if you write it on a piece of paper, probably. So, all right. So what would we want? We wanted to get this. So we have our recursion now. Let's write it down. Let's write down what we got. We got beta k of zk equals the sum over zk plus 1 from 1 to m of beta k plus 1 of zk plus 1 times the emission probability, zk plus 1 given, or xk plus 1 given zk plus 1, times the transition probability, zk plus 1 given zk. Okay, and that's a beta, by the way, there. So make that a little clearer. That's a beta. All right, so this is valid for, what is this? This is valid for k. Here we have a k plus 1. So this is going to be valid for k from 1. So this is for k from 1 to n minus 1. All these things make sense for those k's. But what about when k equals n? Well, or when k equals n minus 1, we end up with a beta of, or beta n of zn. So what is beta n of zn? Beta n of zn equals, oh no, it's not really defined here, because if we had n, then we would have xn plus 1 to n. And what is that? What's going on here? So let's figure out, let's think about the case when k equals n minus 1 and see what we should define beta n to be. So this is the definition. So this is sort of for k equals 1 to n minus 1. And what should we define beta n to be? So when k is n minus 1, what happens here? K is n minus 1. This is xn zk plus 1 given zk. And so here we end up with, when k is n minus 1, this is p of xn given zn. Sorry, that should be an n. Or no, that's, oh right, k is n minus 1, so that's n minus 1. Sorry, I'm botching this. That was n. And this is, all of this still sort of applies. I mean, the only part which was weird was the k plus 2. This becomes zn given zn minus 1. Okay, so we get the transition probability here again. We get the emission probability here again. And so, right, we could just, this thing, we can factor as the product of these, right? We have the probability of this, that, equals the probability of xn given zn times the probability of zn given z minus 1, because there's a conditional independence here. Xn is conditionally independent of zn, so let's check that. Xn should be conditionally independent of zn minus 1 given zn. And yes, that is the case. Xn is conditionally independent of zn minus 1 given zn. So that holds. And so so what this shows us, what we see from this, is that beta n, this would have been beta n in that situation when k was n minus 1. And so beta n should always just be 1. Beta n should always be 1. 1 for all zn. I maybe kind of did that a little bit quickly. So if you want to check that, you can go through that a little more carefully if you'd like. And so for the backward algorithm, we start with beta n. We do this for all zn, and we just go backwards. We do n minus 1, n minus 2, and so on. And the computational complexity is just exactly the same as in the forward algorithm. These recursions just take exactly the same form. So it's big theta of nm squared. And that is the backward algorithm.